In early versions of SQL Server, triggers were the only method available to enforce primary key foreign key relationships, which is also known as referential integrity. SQL Server 6 introduced the ability to create foreign key constraints that enforced referential integrity without triggers, which was called declarative referential integrity, or sometimes just DRI. The role of the triggers at that point moved primarily from enforcing relationships to enforcing business rules that were too complex to be enforced in a check constraint within a table. Some developers continued to use triggers for referential integrity because for a long time they remained the only means of implementing cascading updates and deletes in older versions of SQL servers. Now that SQL Server can enforce the primary foreign key relationships as well as cascading updates and deletes, there's no need to use triggers to enforce referential integrity. But they do remain useful for enforcing complex business rules. Now, there are several types of triggers that can fire on insert, update, and delete statements in SQL Server. After triggers fire after the statement that triggers them executes. These are the most commonly used triggers. They can be created only on tables. Instead of triggers were introduced in SQL Server 2000. They fire instead of the statement that triggers them, executing the specified statement that's defined within the trigger instead of the original statement that caused the trigger to fire. You can use these instead of triggers to validate a condition and then resubmit the original data modification statement. Unlike after triggers, instead of triggers can be created on views. And this is a really cool way of getting around the limitation of updating only a single table at a time if the view definition contains a join between multiple tables. And then finally, there are DDL triggers, which are after triggers that fire after a DDL, or a data definition language statement, executes. And these triggers are created at the database or server level for particular DDL statements, like create table. Now you can create triggers using either Transact SQL code or .NET code. The latter triggers are sometimes referred to as SQL CLR triggers, although they really aren't a separate type of trigger as such. Instead, they provide an alternative way of creating the triggers, any of the triggers that I've listed. You can create these triggers using one of the .NET framework languages, such as C# or Visual Basic. And they're useful if you have to have complex procedural code in a trigger. My focus for right now, though, is on triggers that you create using Transact SQL. Triggers are often used now to enforce business rules that can't be expressed as a constraint and also to raise alerts. Some business rules are just too complex to implement within the expressions available for constraints or rules in a table definition. So triggers can reference values from any column in the affected record, including both the original and the changed values, as well as reference data in other tables or other databases. It really has all of the flexibility of stored procedures. And triggers are also useful for recording changes to data, providing a history of the changes and maybe the user responsible for each change, if that's available, over the connection that's being used in order to access the table. And like stored procedures, triggers can contain complex logic, variables, error handling, and almost the full range of Transact SQL programming. The only limitations on your Transact SQL code within triggers is that you can't create objects or modify their design, and you can't perform some administrative tasks, such as backups. Okay, so triggers are generally a good thing, particularly, as I mentioned, for enforcing complex business rules. But with apologies to Star Trek's Captain Kirk and his trouble with tribbles, there are some trouble with triggers. The biggest risk in using triggers is that users and developers may unknowingly cause hidden data operations when working with data in tables. A trigger is part of the transaction that caused it to fire. So, that transaction is not committed or rolled back until the trigger code is complete. If the transaction is rolled back within trigger code, the outer transaction is rolled back as well. A related problem is that because triggers extend a transaction, there's additional code that is executing within the context of that transaction. They extend the duration of the transaction as well, especially when the transaction accesses other tables. This kind of performance penalty can lower multi-user concurrency to unacceptable levels because it prolongs the time that locks are held. Now, if you need to implement integrity rules that you can't express in constraints, consider enforcing them in a stored procedure instead. The stored procedure can check for a condition and not initiate a transaction if the condition isn't met. This kind of preemptive approach is generally more efficient than a reactive approach, which is what a trigger does because it fires after things generally. And it's far more visible and transparent than the hidden nature of triggers. So, speaking of, another problem is that trigger code is buried deep within a table definition. This obfuscation can lead to debugging problems later because the source of a problem may not be immediately apparent. For that reason, many developers try to avoid using triggers at all because their hidden actions can make maintenance and debugging very difficult, especially if the triggers make changes to tables other than the one that's being explicitly updated by the code that triggered the code execution of the trigger. By forcing all data changes to occur through stored procedures instead of through triggers, you can avoid the need to use triggers at all. If you allow users and client applications to directly update, insert, or delete data using ad hoc queries, triggers are one way, and might be the only way, to maintain control over your data. Let's talk about how triggers work. A trigger uses two virtual tables named inserted and deleted. Those are literally the names of the tables that you access. And it uses those tables to facilitate the actions that you can take in trigger code. When SQL Server fires an insert trigger, it inserts the new row values into the inserted table. For an update trigger, the new row values are copied to the inserted table, and the old row values are copied to the deleted table. So it uses both of those tables together. And then for a delete trigger, the deleted row values are copied to the deleted table. So what you can do within the trigger is examine the combined data in the inserted and deleted tables, and you can see exactly what changes are being made to the data. It's really a pretty slick setup. The nice thing is that triggers can also reference other objects, and you can join other tables to the inserted and deleted tables. For example, to create an audit trail, you could create a trigger that inserts the values in the deleted table into a backup table, and maybe adds the name of the current user and the current date and time. Since the trigger fires each time a row is deleted, there's no other action that's necessary to save the deleted data while removing it from the original database table. You can create triggers for both tables and views. Triggers for tables will fire whenever the data in the table changes. Triggers on views, though, only fire if the data change occurs through that view. And the only kinds of triggers that you can create for views are instead of triggers. Okay, so there's some limitations on that. The basic syntax for creating data triggers is similar to that for a stored procedure. The main difference is the set of options for the object that the trigger is going to execute on, which is going to be a table or a view name. And you also need to specify the type of trigger and the action that triggers the trigger. And then after the as keyword, you include as many transact SQL statements as you need in order to perform the work of the trigger. And then the primary difference between a stored procedure and a trigger is how the object executes. Stored procedures need to be explicitly called, while triggers fire automatically in response to a data modification. All right, so that's the reason for the additional options that you need to define in the create trigger statement. And then triggers also don't support parameters because they obtain their source data from the inserted and deleted tables. Okay, so what I'm going to do is I'm going to use the Northwind database, and create this test trigger table. And it has a single column called signal, and it's type string varchar 50. So I'll execute that, and we now have that table within the Northwind database. And I'll insert a couple of values into the table. So now we have stop and we have go, some sort of a signaling kind of application. Okay, now I want to create a trigger on that table. So what this trigger needs to do is check the value of the signal column in the deleted table. It's going to raise an error and rolls back the transaction if the value is stop. All right, so there's several things to notice about this definition. So it uses the create trigger statement, giving it a unique name, and it's going to execute on the test trigger table. Remember that a trigger is going to execute based on a single object, a table or a view within the database, at least for data modification triggers. Okay. Trigger is a database object like any other object, and so it has to have a unique name within the schema. Okay. Then you have the on clause to identify it with the table. And then this particular trigger is going to happen when you attempt to delete rows from the target table. So this is an after trigger, and it's going to fire on delete actions. This particular trigger, the way it's written, assumes that there's only a single row in the deleted table. And so it's going to save the value of signal from deleted using this statement right here. Now this is a bit of a derived scenario for this simple trigger, but it works here. But if it's possible that a user could attempt to delete multiple rows, which is the most common situation, then you would have to write the code differently from this simple example in order to be able to manage that situation. So instead of checking for just stop values, I would have to write a different kind of a query here in order to find if maybe any of the rows are trying to delete stop values. So there's certainly ways of doing it, but I keep things simple here. Okay, so if the test value is stop, remember that's that test value that I read from the signal column from the deleted tables, then I'm going to print out a message because deleting stop signals is a safety violation and so is not allowed. Go signals, no problem. Stop signals we don't want to delete. And then in that case, we roll back the transaction. Okay, so first need to create the trigger, and then I can test it. So here's an example of attempting to delete a stop. And as you can see, when I executed this statement, the trigger fired. I get that print statement that I defined within the trigger, and then it rolled back the transaction, which causes SQL Server to raise this exception. Transaction ended in the trigger. The batch has been aborted. And I still have that stop row within the signal table. All right, if I no longer need the trigger, I can go ahead and drop it using this code right here. It just requires a drop trigger statement and the name of the trigger. And notice that you don't have to specify the table name or type of trigger when dropping it, because this name uniquely identifies it. So I'll go ahead and execute that. And now that trigger no longer exists, and if I wanted to delete the stop record, I could go ahead and do that. Back in the old days of versions of SQL Server before SQL Server 2000, you could define triggers on tables only. The trigger code then executed whenever its triggering action occurred. Rows were inserted, updated, or deleted, whatever. So the idea behind an instead of trigger is that it fires instead of the insert, update, or delete statements that triggers it. And you can define code that completely supplants, replaces the specified action on the table. So this is, well, when I first encountered instead of triggers, I was really leery. I was already concerned about the hidden nature of triggers. But instead of triggers is now I would execute a line of code against a table, and that code wouldn't be executed at all. Instead, the instead of trigger would execute, and that's kind of hidden. But instead of triggers have a definite place because you can use them with views. And that's the big difference. That's really the big benefit of using this kind of trigger. So in other words, what that means is that you can update tables and views that would normally not be updatable by using an instead of trigger. An instead of trigger can support inserts, updates, and deletes that reference data in more than one table, which you can't do directly on a view. And they also enable you to code complex logic that will be applied whenever the view or table is modified. So you can present a friendly interface through a view, and behind the scenes, any updates to that simple view could be propagated to many different underlying tables. Okay, for an example, let's look at creating a categories and products view here. So this selects some information from products and joins on categories. So I'll go ahead and create that view in the Northwind database. Okay, so we have that view. Now, because this view contains a join between the products and the category tables, this normally allows you to update only one or the other table at a time, not both, in a single update statement. So once I have that view, I can't execute code like this. The reason being is that I'm trying to update data in the products table as well as within the categories table. And I get this error message, viewer function blah, 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 is not updatable because the modification affects multiple base tables. So if we want to allow users to be able to perform this kind of an action using this view as it's defined, we can define an instead of trigger. And here's a trigger that does exactly that. So what this code is going to do is independently update each table anytime a user attempts to update multiple tables using the view. In fact, not even multiple tables. Anytime the user attempts to update data in either of those tables. In that case, the trigger takes over and performs two separate updates instead of the normal course, which is a single illegal update. And so this is going to show how you can substitute more complex logic for the original update action. All right, so the trigger is called Categories and Products Update. It's on this view. So again, it's associated with a single object, table, or view within the database. And it's going to be instead of the update statement. And so now we know it's not an after trigger, it's an instead of trigger because of this clause right here. All right, so we set no count on. And here's the first update statement. All right, so there's a little bit of logic here for handling how this works. So we're first going to update the products table, going to set the product name to the new value of product name. In this case, there's no parameter that was passed into the trigger. Triggers don't have parameters. And so we have to get that from the inserted table. It's an update statement that this trigger is firing in response to. And so the new values, remember, are in the inserted table. So I can use the inserted table there, get the product name. And then I'm going to use that value to update the product name here. And then I need a where clause so that I update the correct row in the table. And I get the product ID from the product ID value in the inserted table in order to filter that value. Okay, so make sure that you understand that logic, because again, I get the product ID, which doesn't change because it's the primary key of the table. And then I use the product name in order to update that value in the set clause of the update statement. Okay, the categories table is the same basic logic, but there's a twist to it. So the twist is that in the products update, it doesn't matter where the product ID came from, inserted or deleted, because both those tables are going to have the same value, because that's not changing. But for the categories table, the code needs to filter the table on the old value, so it's using the value from the deleted table instead of the inserted table. And the reason for that is that the inserted value doesn't exist yet. So it has to get the category name for the filter from the deleted value. Okay, so let me re-say that because it's very important. The product ID doesn't exist yet, so we have to get the old category name from deleted and use that to filter the records rather than linking on the new product ID because that doesn't exist yet. So the net result of this trigger definition is that although a single update statement that tries to update both the product and the categories tables through a view would otherwise fail, the instead of trigger fires instead of the normal update statement and explicitly writes the changes back to both tables. Because that original update statement never gets a chance to execute, SQL Server doesn't raise an error as a result of that statement. Instead, this code within the trigger executes. And it doesn't cause an error, so it happily executes. The nice thing is that the user or client application doesn't even have to know about the underlying tables or their relationship. Okay, so I'll go ahead and create the trigger. Don't think I've created it yet. There we go. And now we can execute this statement, this kind of update statement, that updates two tables at once. Can execute that, and it executes successfully. So as you can see, instead of triggers can make views very powerful, allowing actions that would otherwise not normally be permitted. You could also use instead of triggers to call stored procedures to perform requested data modification. And quite frankly, this is a very useful feature that probably will tempt developers who previously have been dead set against using triggers in the past to take a second look. And certainly I've come around to that way of thinking. It's still a risk to use triggers because it's hidden code that's executing, but there's some situations where they can be extremely useful. There's another broad class of triggers that you can create in SQL Server called DDL triggers. These are data definition language triggers that respond to DDL events, which are schema changes within the database. And these are the kind of changes that you make using create, alter, and drop statements. And these are useful for administrative tasks, things like auditing and regulating database operations that change the database schema. Because changing a database schema is a pretty fundamental action that can break a lot of applications. So you may want to have control over them. So there's several different kinds of scenarios where you might want to use DDL triggers. You might want to prevent certain changes to your database schema, certain types of changes. You may want something to occur in the database in response to a change in your database schema. And probably the most common thing here is to log the change. Allow the change, but log it someplace. And then you also might want to record changes or events in the database schema. So various ways that you can use this feature. DDL triggers fire only after the DDL statements that trigger them. So they're essentially after triggers. Each DDL statement raises an event. In order to use DDL triggers effectively, you need to understand the database scope in which a particular Transact SQL DDL statement executes. For example, the create table and create procedure events map to the create table and create procedure statements, and both have database scope. And you can look in SQL Server books online, and specifically the DDL events topic that contains the complete list of events and the scope of each. So in this example of a trigger, it shows how you can create a database trigger that prevents the addition of new tables. All right, so if you execute this code, it creates a trigger called no new tables. It's on the database, so it's at the database level, database scope. And it's for create table. Notice that most of the time, the event that you're linking into is the same name as the T-SQL statement, but with an underscore instead of a space between the name. And in this case, all I'm going to do is I'm going to print a statement saying no new tables allowed in this database, and then roll back the transaction. And the nice thing here is that this works even if you don't create an explicit transaction in order to perform this action. Okay, so you can roll back the transaction within this trigger. All right, so I'll go ahead and create the trigger within the Northwind database. And then I'll once again go in and try to create a table called test DDL trigger, execute that, and it fails, and I get the message no new tables allowed in this database, and I get an exception raised because SQL Server rolled back the transaction in response to the trigger. So that's how they work. If you need to temporarily disable the trigger, you can use the disable trigger statement here and specify the trigger name and the scope of it. And now I can go in and attempt to execute that statement again, and it successfully executes. The syntax for dropping a DDL trigger is a little bit different from a DML trigger because you have to include the scope of the trigger. So drop trigger, no new tables, the name that gave it when you created it, on the database. And I can execute that, and now that trigger will no longer execute.